In this video, we're going to talk about reaction quotient and how it can be used to determine a shift towards equilibrium. So we're going to start by looking at what is a reaction quotient. So the reaction quotient is represented by the letter Q, and it's a measure of the relative concentrations of products and reactants in a reaction at a given time. So if we consider kind of our standard reaction that we've been using to date, so AA plus BB forming CC and DD. So we've stated previously that the equilibrium constant for this reaction can be calculated by multiplying the equilibrium concentrations of the products raised to their coefficients and dividing by the equilibrium concentrations of the reactants raised to their coefficients. So what we're not writing in here, but we could, is that these are equilibrium concentrations. So this is when the reaction has already reached equal forward and reverse rates of reaction. Q is going to be calculated in nearly the exact same manner. So it's going to look like the same calculation. And the reason that it looks like the same calculation is because it allows us to then compare Q and K. But unlike K, these are just concentrations at a given time. So they're not necessarily at equilibrium. And so we can compare Q and K to determine which way a reaction will proceed to get to equilibrium. We are going to be comparing the values of Q and K to interpret which way our reaction will shift to reach equilibrium. So I've represented the value of Q and K as kind of a bar graph. The taller the bar, the bigger the value. So we see K is constant, which makes sense for a given reaction, and the value of Q is changing depending on where in the reaction we are. So by comparing the relative heights of these two boxes, we can talk about which way a reaction will shift. We're going to start in the middle here, where Q is equal to K. Since Q is measured the same way as K, if the two are equal, this is a system at equilibrium. And so no shift will occur to reach equilibrium because it's already there. If we go to the left, we see here that Q is less than K. This system is not at equilibrium. So as a reminder, both of these values are calculated by looking at the concentration of the products raised to their coefficient over the concentration of the reactants raised to their coefficient. And so if Q is too small, it means that we don't have enough product yet in our reaction. And so the reaction is going to have to shift right to produce more product to reach equilibrium. If, on the other hand, Q is much, much bigger than K, or Q is larger than K, if we go back to our reaction, so we know that this is not at equilibrium either. And if we go back to our equation at the top, what we'll see is that because Q is much bigger than K, we have too much product in our reaction system. And so we need to shift left to get rid of some of that those products and reduce the value of K. So this is going to shift left to remove product to reach equilibrium. And we would use a Q value if we had the initial concentration of all of the chemical species in an equilibrium. So we're going to look at that next. Consider the following equilibrium system. So we have nitrogen gas plus oxygen gas forming nitrogen monoxide gas, and the KEQ value for this is 0.52. If nitrogen gas, oxygen gas, and nitrogen monoxide were added at equal concentrations of 1 mole per liter to an empty flask, what is the equilibrium concentration of nitrogen monoxide? So we're going to start by writing down our ICE table. So we'll have our reaction written again. And ICE. So our initial concentrations are all 1.0. So anytime we have initial concentrations in all three for all of our species, we're going to calculate Q to figure out which side will decrease in concentration and which side will increase in concentration. So Q is going to equal the concentration of nitrogen monoxide squared over the concentration of nitrogen times oxygen. So this is going to equal 1.0 squared over 1 times 1, and we get a Q value of 1. If we compare that to K of 0.52, we see that Q is bigger than K. Therefore, the reaction will shift left to remove some of the product, meaning that it's going to be an increase in the concentration of our reactants and a decrease in the concentration of our product. So when we fill in our ICE table, our reactants will have a positive change and our product will have a negative change. And we're again going to use x's here. So this is going to be minus 2x plus x plus x. So on this side now we have 1 plus x on our reactant side, and our product side will have 1 minus 2x. So when we plug this into our equilibrium expression, KEQ equals NO squared over N2 times O2, and we plug in our values, so 0.52 equals 1 minus 2x all squared. And then we can, because these two values are the same, N2 and O2 is going to be the same as just writing N2 squared in terms of concentration. So we can list the bottom as 1 plus x squared. So because we have squares on both sides there, we can take the square root to cancel out our squares on the top and bottom of that fraction. I'm going to write down rounded numbers, but I'm going to keep the full number in my calculator. So the square root of 0.52 is 0.72, and that's going to equal 1 minus 2x over 1 plus x. So I'm just going to leave out the decimals so it's easier to write. We're going to rearrange this, so our denominator must stay together. So we're going to take this 1 plus x value and we're going to multiply it by 0.72, each term by 0.72. So 1 times 0.72 is 0.72, and x times 0.72 is also 0.72x. That equals 1 minus 2x. So in order to group things together, we're going to move our 0.72 to this side of the equation and our x this way so that we get positive x's. So we're going to have 2.72x equals 0.28. And so to solve for x, we're just going to divide 0.28 by 2.72. And we get 0.102. So I'm not really maintaining sig digs here, so that's moles per liter. We're now going to plug that x value back in to solve for our equilibrium concentrations. So the equilibrium concentration of nitrogen is 1 plus x, so it will be 1.10. The equilibrium concentration of oxygen will be the same as nitrogen. And the equilibrium concentration of nitrogen monoxide will be 1 minus 2x, which is 0.80 with rounding. Okay, so our second example, what is the equilibrium concentration of hydrogen gas if initially 0.5 moles per liter hydrogen and iodine gas and 0.6 moles per liter hydrogen iodide gas were added to an empty flask to establish the following equilibrium? So we have our equilibrium equation with a KEQ of 3.75. So we can construct our ICE table here, ICE, and we can fill in our known values. So we know that our initial concentrations are 0.50 for both of our reactants and 0.60 for our product. So we're now going to take these numbers and we're going to calculate Q. So Q is going to equal the concentration of hydrogen iodide over the concentration of hydrogen times iodine at our initial point in the reaction. So 0.60 over 0.50 squared. And we get 1.44. So comparing to K, we see that Q is less than K, so the reaction will proceed to the right to increase the concentration of products. That means that we will have a negative change for our reactants and a positive change for our product. So we can fill in those signs now. We're going to represent our change as x, so it'll be x for these two and 2x because of the coefficient here, giving us equilibrium concentrations of 0.50 minus x and 0.60 plus 2x. So we can write our equilibrium expression now and plug in our numbers. So 3.75 is going to equal 0.60 plus 2x squared over, and I'm going to combine H2 and I2 because they have the same value at equilibrium to write 0.50 minus x squared. So I'm going to take the square root of both sides here to get rid of those exponents, make this easier to solve. And again, I'm going to write a rounded number down, but I'm not going to round in my actual calculator. So I'm going to have a 1.94. It's going to equal 0.60 plus 2x divided by 0.50 minus x. And again, we're going to take this bottom term, move it up and distribute the 1.94. So that's going to be 0.97 minus 1.94x equals 0.60 plus 2x. So we're going to move the 0.6 over this way and the 1.94 over that way so that we have positive x values. So our next step is going to be 0.37. So that's 0.97 minus 0.6 equals 3.94x. So that's 2 plus 1.94. So x is going to equal 0.37 divided by 3.94. And we get 0.094 moles per liter for our x value. So the question is asking what is the equilibrium concentration of H2. So we're going to plug this back into our equilibrium concentration for H2. So 0.50 minus X. And we get 0.41 moles per liter.